In this video, I will derive the pressure dependence of enthalpy, delta H over delta P under constant temperature condition. First, du equals TdS minus PdV, and then by definition, H equals U plus PV, therefore dH equals TdS plus VdP. Now we're going to plug in this expression of dH in here. Delta H is T delta S plus V delta P. So we have two terms here. And then we're going to separate these two terms. The first term is T times delta S over delta P under constant temperature condition, right here. The second term is simply just volume. And then we are going to prove one of the Maxwell relations, starting from dG equals negative S dt plus VdP. This is from the definition of G. G equals H minus Ts. And then, given this equation, we have delta G over delta T under constant pressure condition equals negative S, and delta G over delta P equals volume under constant temperature condition. So we have these two equations. And because G is a state function, the second derivative of G with respect to T and then P is equal to the second derivative of G with respect to P first and then T. And therefore, we can plug in this delta G over delta T equals negative S here, delta G over delta P equals volume here, and then we have one of these Maxwell relations, negative delta S over delta P equals delta V over delta T. Pay attention to the subscripts. And then we can use this equation to simplify this. Therefore, delta H over delta P equals T times delta S over delta P at a constant temperature condition plus volume equals volume minus T times this derivative, delta V over delta T under constant pressure condition. This is much simpler because P, V, T are easily measurable, entropy is not. And then because of the definition of beta, beta is 1 over V times delta V over delta T under constant pressure condition. This equation can be simplified to be V minus T times beta times V equals V times parenthesis 1 minus T beta parenthesis. For ideal gas, we can evaluate this pressure dependence of enthalpy easily by using this equation, because for an ideal gas, delta V over delta T equals nR over P, and nR over P equals V over T. Therefore, we have V minus T times V over T, which is V minus V equals 0. So for ideal gas, enthalpy does not depend on pressure under constant temperature condition. For real gas, okay, enthalpy does depend on pressure, but to evaluate this, we need the equation of state. For example, given the van der Waals equation of state, we just plug in the function of volume as a function of temperature, and then we evaluate this first derivative, do a multiplication, and usually for a real gas, this delta H over delta P is non-zero. For liquid or solid, we can use this equation because usually beta is a constant for liquid or solid. It does not change significantly. Even if you change the pressure or temperature, beta remains a constant approximately. And usually beta is a very small constant, and T times beta is much smaller than 1. So in a lot of situations, we have delta H over delta P under constant temperature condition is approximately equal to volume. This holds true especially for solids. Again, for solids, beta is particularly small.